To begin with, first of all, I'm very sorry that I cannot see everyone in person in the UK. I love traveling to the UK. I'm a bit tired of this pandemic because I love to see Anders and some of you. But it's good that we have this event online. And the second thing I wanted to say is that I think my colleague Curtis gave me a very good segue, because at the end of the lecture,
015 is not available. At the tone, please
that's
record your
not
message.
me.
When you have finished recording, you
somebody
may hang up
perhaps
or press
muted.
1 for more options.
Okay. So there was during the Q&A, Curtis mentioned the need for calibration of some AI tools. And this is exactly what we're going to discuss today. Perhaps it's not exactly the kind of calibration that Curtis would like to see, but it's calibration nevertheless. So before I get started, I want to say that most of what you'll hear today is joint work with two wonderful young people, Li Wale from Stanford and Isaac Gibbs also from Stanford. So I think I don't need to explain this crowd that, you know, we use AI systems to make critical decisions, you know, and we had a wonderful talk about this just a minute ago. So I don't think I need to get into tell you about the importance of AI. And so, of course, we use these systems to trigger decisions, to trigger perhaps medical diagnostics. And the question is, of course, whether we can have confidence in this prediction. And that's a very important topic and the subject of this workshop. And, you know, I think it was mentioned by Anders and Curtis that, you know, we cannot really assume that your favorite deep network is well calibrated. And there's a lot of literature on this. You see a paper from 2017 who just, even on very well curated data sets, things that are extremely well understood, that have been analyzed to death, that somehow neural networks are a bit too sure about themselves and about their predictions. And so this is a problem. And this is a problem because, you know, we use these systems in very sensitive applications. There are applications outside of medicine. We use AI systems to rank the CVs of applicants to decide whether or not you're going to get bail or paroled. And so we tend to use these black boxes a bit too faithfully. And so I think it's important to understand the calibration of these tools and to assess a bit of uncertainty and do a bit of uncertainty quantification. So the question I'd like is, like, to me as a statistician, a point estimate about a future observation does not say very much. What I would like to know is how confident you are about your prediction. And so if we think about, you know, the way the world is going, where more and more things get automated or at least partially automated, we can imagine a hypothetical scenario, and I'm not saying that this occurs in practice, where, let's say, students apply to colleges. And so because we receive so many applications at Stanford, it's in excess of 70,000 at the moment, we might actually resort to some form of AI to sort the applications. And so maybe there's an outcome of interest I'm interested to predict, and maybe the AI system will predict perhaps how well I'm going to do if admitted to Stanford. But of course, a point prediction, let's say your GPA after 2 years of undergraduate education based on various attributes, doesn't tell decision makers very much. And so the question I'd like to ask in this lecture is, why don't we see a form of uncertainty quantification a bit more often? In particular, and this is very different from the type of confidence interval that you've perhaps been used to think about in the literature on statistics, is why don't we see prediction intervals more often? So you see, I want to predict a label Y, I have features X. And what I want to know is, I want to be able to construct from the data I've gathered so far from the experience of others, to quote my colleague Brad Efron, I want to be able to construct a predicted range for the values, the likely values of the label. And so it's not a confidence interval in the statistical sense. That is, I'm trying to predict an outcome that is directly observable. And so it would be fantastic if somehow I could actually give decision makers or doctors or whoever has to make a decision, a notion of confidence about what I've learned from past data in the form of a prediction interval, which we're going to formalize a bit later, but right now it's a list of possible labels that contain the true label 90% of the time. And one of the reasons we might not see this very much is that, as you know, we are way past simple regressions. It's not completely unclear when the data generation distribution mechanism is unknown, when we use algorithms that are extremely sophisticated, how we could possibly construct, do uncertainty quantification. And what I'm here to argue is that there is a wonderful field at the moment, which is exploding with activity. And this has a name of conformal inference. And in fact, as I'll mention in a minute, this field was essentially started by a colleague of yours in London, namely Vladimir Vogt, whose work has influenced me enormously over the last few years. And so what the work I'm about to describe is that you have a predictive model, a predictor, maybe it's a very complicated neural net, or maybe it's XGBoost or whatever you want. It doesn't matter how complicated it is. And you want to make, I'm going to say UQ, uncertainty quantification about your neural net. And of course, one solution is to open the black box. But honestly, I mean, this is extremely problematic. Instead, what we're going to do is we're going to work around the black box and build what I'm going to call a protection layer so that I can use the black box safely. And so the way conformal inference operates is that I'm giving you training samples, xi, yi. There's a test point that comes from the same distribution. And what we've learned since the fundamental work of Vladimir Vogt and his colleagues is that we know how now to construct prediction intervals that are intervals C hat of x that have been constructed from past data that will contain the true label 90% of the time. And what's remarkable about this is that it holds infinite samples for any distribution of features and response, x, y, and any predictive algorithm, f hat, no matter how complicated. And so this is a piece of technology that we have that allows you to do these things. Now, the first time I think you hear about this, you are a bit surprised that if I make no modeling assumption about the distribution of x and y, and no modeling assumption, and no assumption about this predictive model, how come I can construct predictive intervals in this fashion? And in this lecture, I'm going to give you a primer on conformal inference. And of course, the ideas go back to Vladimir Vogt and his colleagues. Then we're going to discuss an elephant in the room in machine learning, which is what happens under distribution shifts. And finally, we're going to talk about controlling other metrics other than miscoverage. Okay, so I'm going to talk to you about conformal inference, and there are many algorithms to implement conformal inference. The first ones, as I mentioned many times, being proposed by Vladimir Vogt. Here, I'm going to introduce what I believe is perhaps a better algorithm to implement conformal inference, which we call conformalized quantile regression. And this is joint work with Yaniv Romano and Evan Patterson. So my goal in this first part is to give you a sense of what conformal inference is about. So the goal is very simple. We have training data x1, y1, xn, yn. We have a test point xn plus 1. And from the training data, I want to create a set of labels, C of x, that contain the true label of precise fraction of the time. And I want this to hold no matter the distribution of x and y, which is unknown, no matter the sample size, I want this to be always true. And so what I want to be able to say, thinking a little bit about, real application, some of the stylized application I mentioned before, is that I want to be able to say that based on the candidate's high school identifier and GPA and ACT scores and other attributes like extracurricular activities and so on, I want to predict how well the student I want to say that the college GPA is predicted to fall in a range, and I want to be correct 90 or 95% of the time. And this you control. And how can you possibly do this? So just to give you an idea about conformal inference, of course, I can only plot in 2D. So in 2D, I have a response Y and I have a predictor X. And so I may have collected data, which are the black dots that you see on my figure. And of course, if I knew the conditional distribution of Y given X, that is, I would know these red curves, which are the likelihood of Y given the hypothesized value of X, then of course I might be able to calculate the 95th percentile, the 5th percentile. For each value of X, I would do this and I would connect the dots and I would get a perfectly valid prediction interval. But of course, two things jump to your attention. First, in this example, the length of the prediction intervals would vary. And the second is, well, that's assuming that machine learning has been solved, that somehow the distribution of Y given X is known, which is totally, we know that that's not the case. So in reality, all you have is you have a sample, and I want to be able to give you the kind of guarantees that you would get if you knew the conditional distribution. And so this is all we have. And one thing you could try to do is to use, instead, repurpose your neural net, not to fit the conditional mean, but instead the conditional quantiles. And the way you would implement this is absolutely straightforward. You'd say, well, let me change the loss. Instead of using a squared loss, which is essentially trying to find the conditional mean, let's use what is known in machine learning as a pinball loss. And of course, these ideas goes back to Kunker and Bassett from 78. Let's use a different loss function. And the loss function is the pinball loss that you see on the right, if you can see my little hand. And it has, it looks like if alpha is 0.5, this is just the absolute value. And if alpha is not 0.5, then the absolute value is going to be tilted to the left or to the right. And so if you think for a second that alpha is 0.5, so that your loss is just the absolute value, then basically you're trying to minimize the sum of the magnitude of the residual, which you're trying to find a conditional median. And by adjusting the slopes, you would try to find the conditional quantiles. So by fixing alpha to be 0.05, I can try to find the lowest conditional quantile, which is a black curve you see at the bottom. By fitting alpha to be 0.95, you might find the upper quantile, which is the upper curve. And you might hope that this will actually give you a sense of uncertainty. And does this work? And of course, it's not because you fit quantiles that you'll become all of a sudden well calibrated. You are not. And just for this crowd, let's imagine that you fit a neural net. Well, the tendency these days, from what I understand, is that you fit a neural net to zero training error, in which case your two quantile functions will actually be the same. And so the predictive accuracy will be 0. And so here I use an example, which is not as extreme as this one, but we train a neural net a bit regularized so that it does not do crazy things. And so we got two quantiles, and then we can see what I just told you before, that the neural net is a bit too sure about itself. That is, on data that has not yet been seen, I want a 90% coverage, but I don't get 90%. I get about 66% coverage, meaning that I was expecting 10% of these red dots that I've not seen before to fall outside of the band, and when in fact it's more like 33%. Okay, so this is, going back to the calibration problem. The amazing thing is that there's one way to correct this, and this is where the amazing work of Kunker and Bassett on quantile regression meets the work of Vladimir Vogt on conformal inference. So what you can do is you can fix this problem by a little twist that I'm going to explain now. And what you do is, you get your training sample, and what you're going to do is you're going to just perform quantile regression, perhaps again with your neural net, on the first half of your training sample, the first split. And then you have reserved the calibration set. And the calibration set you have reserved is on the right. It's this set of green points. And what you're going to do is you're going to project your quantiles on these green points, and you're going to score how well you do. And so the scoring mechanism is going to be simple. There might be many ways you score. I'm going to show you one way, which is this. I take a point that I have not seen, a calibration point, and I'm going to record its distance to the nearest quantile function. And this distance is going to be positive if the point is outside of the predicted band, and it's going to be negative if it's inside. So moving on to the next slide, this is exactly the formula at the top is exactly what I mentioned. I've got, let's say, 300 calibration points here. I got 300 scores. The scores are positive if I'm outside of the prediction band. They are negative if I'm inside the prediction band. And so I got 300 scores like this. And based on these scores, I can draw a histogram of these scores, okay, which is a histogram you see on the right. So these are the histogram of these 300 scores. And then what I can do is I can look at the 90th percentile of these scores. And this is what I'm doing. So I'm calculating 300 scores. I'm looking at the 90th percentiles of the scores. And now I'm going to basically shift the projected band up or down by this quantile Q. And so what we see from this is that it's quite simple. It's actually very simple to implement. If somehow the neural net did a good job at calibration in the first place, then I would expect 10% of the point to lie outside, 90% to lie inside. Therefore, the 90th percentile might be 0, in which case I would not touch them because they're already quite good. If, on the other hand, the neural net was or too confident, which is something that we see often when we play with data, then there would be more points outside, the quantile would be positive, and then, of course, that would enlarge the confidence band. If, on the other hand, you're a bit like me, you're trained in statistics, so you're a bit conservative by nature, you might actually see that you are too conservative to start with, in which case Q would be negative, and the method would realize that you're too conservative and would actually shrink the prediction bands. Okay, so this is a construction. This is very simple, and when we test it on data, we can see that the coverage is spot on. Like you want 90%, and you get 90.09% in this case, which is just too good to be true. Well, it's not too good to be true because it's actually a theorem, and that's the main theorem in the field of conformal inference applied to the specific algorithm, which says this, that no matter what algorithm you use to learn the quantiles, no matter the distribution of the data, no matter the sample size, no matter the dimensionality, no matter anything, the coverage of this method, the unknown labels, will be within range exactly 90% of the time. Not 92, not 88, exactly 90% of the time. And so this is quite remarkable. And so this is a method that you can deploy in a lot of applications. And before we do this, just to a bit contrast the algorithm that implements conformal inference with what people were doing perhaps before. This is an implementation of conformal inference. This is actually fitting intervals of constant widths. It's a theorem that the coverage should be 90%. This is the algorithm you've seen, where essentially by fitting quantiles, you learn about the heteroscedasticity in your data. It's a theorem that the coverage is 90%. But what you can see on the right is that you have an implementation where you have a very adaptive algorithm where the width of the intervals varies a lot as you move in X space, whereas it doesn't move on the left. And so the CQR implementation is highly adaptive, while the classical implementation is not. So it might be a bit of a little improvement. Okay, so now that you have a method which makes no assumption of any kind, then you can project uncertainty. And so we've applied it to, for example, predict utilization of medical services. We use a medical expenditure panel survey of 2016, where the goal is to predict healthcare system utilization as measured by perhaps the number of visits to a doctor's office or hospital or so on, as a function of a lot of variables: your age, your marital status, your poverty status, your race, functional limitations, and so on. And so these are very boring plots because you want to project healthcare utilization, you want 90% coverage, and no matter what algorithm conformal inference algorithm you use, you're going to get 90%. The advantage of the implementation you've seen is that it is better at doing conditional coverage because it's more adaptive. So I'm not going to get into this today. And because it's more adaptive, you get tighter prediction bands. And so it's something you can use, and this is something you can use for anything you like under the sun. And one of the things that are very, very boring about this method is that you want 90% coverage, and no matter what you do, you get exactly 90% coverage. So, there are many implementations of conformal inference. I showed you one, but what's good is that you can really construct valid prediction sets. And so that's good news. Just as a little interlude, because this method does not make a lot of assumptions, this was used by the Washington Post, the CQR algorithm, with an enormous variation, which I won't have time to discuss, but to actually predict the outcome of the US election and also the outcomes of current elections. So, for example, the one that we had in Virginia last month. But for example, this algorithm was used to predict the outcome of the election in various states, including, of course, the pivotal states of Pennsylvania, where, of course, the election ballots had been cast already. And so what the problem was, well, you have some training data. And what are the training points in this example? There are the counties that have reported. And what do you need to predict? You need to predict the outstanding votes in the counties that have not been reported. And you need to do this with confidence. And of course, this is an example where getting it wrong has enormous consequences. And so Bronner and Shirian, who are at the top of the slides, I hope you can see their names, actually implemented a variation of CQR. I'm going to not discuss what they've done, but here is a snapshot of the Washington Post on November 5th, 2020, where you would actually, the Washington Post was communicating to its reader in real time where it thought that the election would end up. And so they use a very beautiful way of displaying uncertainty using this sort of color scheme where you can be dark or different shades of blue and different shades of red. And of course, the darkest point are like the median. And as you go to the lighter shade, you look at the quantiles of the projections. And so they use these algorithms to inform their readers about what they think would happen with uncertainty built in when at the end, when every vote will be tallied. Okay, so all right. So now I can take questions now, or I can move on. Anders, is up to you.
Right now, I think we'll just continue and we'll take questions afterwards. Yeah.
All right. Okay, so I want to discuss two things that are more recent, and this was a bit what was being discussed at machine learning conferences about 2-3 years ago, and now I want to discuss some more recent things. Okay, so I think, and the reason I decided to discuss this today is that I think that a lot of machine learning folks are concerned about this, which is how do we move beyond exchangeability? So the key assumption in a lot of machine learning literature and algorithms we use days in and days out is that the training sample I got is somehow representative of future samples. But this may not be the case. And in fact, in a lot of applications, that will not be the case. So if we want to deploy a model in a new environment, maybe I have trained a model on American patients, but I want to deploy it in France. And of course, I'm going to have a shift in the distribution of patients. Or maybe the environment is dynamic. Like, let's say, the most dynamic environment we can think of maybe is the stock market behavior, which will shift in response to world events, for example, in response to the pandemic. And the stock market is definitely not stationary, let alone IID. So I think one research project we started to work on with Isaac Gibbs is, okay, now maybe we have a data stream, XT-YT, where perhaps XT-YT has a distribution PT, which is varying across time. And maybe I don't have a good reason to believe that these data points are exchangeable or IID. And yet I still want to use past data to make a prediction about the future. And so I want to construct at each time point t a prediction set C hat t for YT, the unobserved labels. And at the minimum, I would like to guarantee that YT belongs in the prediction set at least 1 minus alpha fraction of the time. I could be more ambitious and want to guarantee that, really at any given time, the chance that C hat t contains the true label is 1 minus alpha. Okay. And this is challenging because now, things will change with time. So how do we deal with this? So what makes conformal inference work is that when I said before that I had a calibration set, the calibration set, if I assume everything is IID, the calibration set is representative of future samples. So by looking at the outcome of my algorithm on the calibration set, it is predictive of what I will observe on future test points. Because, I'm sorry to use a term, but because the calibration set is exchangeable with future test points. In other words, if I look at the quantile of some statistics on the calibration set, then basically I would have an alignment between the calibration set and the future test point. What's different here is that when we have covariate distribution shifts, it is no longer the case that what you've observed in the past is representative of what you'll observe in the future. And therefore, the data that you're going to use to calibrate your algorithm may not be aligned with future test samples. Nevertheless, so maybe the histogram will be shifted to the left. Maybe it will be shifted to the right. You don't know. You're going to have some shifts that you're going to have to deal with. But what this is saying is that when I'm calibrating, I'm looking at the quantile of my calibration values. And still, what we can think is we can think about a knob where, what this is saying, depending on the shift, is like to maintain valid coverage, I should turn this knob and use not the value, the nominal value of the quantile 1 minus alpha, but perhaps a value which is adapted to the shifts. That there's really one parameter that I need to know, which is which quantile of the calibration data should I use? And if it's shifted to the right like this, maybe I should use a higher quantile. If it's shifted to the left, maybe I should use a lower quantile. And so here we're looking at something interesting, which is that we're looking at a learning problem. That is, and it's a learning problem in a very low dimension, which is you can think about trying to adapt to distribution shifts as learning the quantile that you should be using. You should not be using the nominal quantile because it's not representative of the future. You might want to dial your quantiles up and down depending on what you see. And so the key idea we had with Isaac was to, well, if I knew the distribution shifts, then I could use sort of the oracle quantile, alpha star, but I don't know it. So can we learn it? Can we learn it from data? And so what we proposed is a very simple algorithm that would essentially try to adapt as we go along the quantiles of the calibration data that we should use. And we propose fitting alpha t using an online update where alpha t plus 1 is equal. So the alpha at the quantile I'm going to use at the next time point depends on the errors I've observed. And so the quantiles at time t plus 1 is the quantiles I used yesterday plus gamma times the nominal, the target alpha minus the error. And what is an error? Of course, it's an error is whether I covered at time t or not. And so what we can see is as I start to make a lot of errors, somehow it's indicating that I'm not using the right quantiles. So this quantity will become negative, and so alpha will decrease, or 1 minus alpha will increase. It says you have to increase the size of your intervals. And conversely, if I'm right too often, then this term will become positive because the error process tends to be 0. And so alpha will increase, and this will say that, you know, I'm too conservative. I should reduce the size of the intervals. I have an opportunity to be less conservative and more precise in my predictions. So these are very simple update rules, which takes this form. And if some of you are working in online learning, it has a flavor of, it feels a bit connected to online learning, and especially on online gradient descent, and you would be correct in this assumption. The interpretation is not straightforward, but what you're looking at is essentially an online gradient descent algorithm with respect to a pinball loss, the pinball loss that we've introduced before. So it can be interpreted in the terms you know. And of course, unless if you come from a different field, namely control theory, you know, basically there's an error process that you try to control, and you have a knob, which is alpha, and you try to turn this dial up or down this knob to bring your error process close to the desired target. Okay, so this is and sort of an online descent algorithm, and we applied it to the stock market. And so the stock market, as I mentioned before, is a very dynamic environment. Certainly, stock prices are not IID in time. You know, we go through periods of low and so-called high volatility. People remember the 2008 crisis. People, of course, know about the effect of the pandemic on stock prices in 2020. We saw enormous swings in prices that we had never seen before. And if I'm trying to predict the volatility of stock prices, then we have, well, essentially two methods. One, which will apply conformal inference out of the box without trying to adapt the quantiles I'm using. And if you were to do this, you know, for like you would get an average local error rate, a local miscoverage error rate, which is given by the red curve that you see here. So let's look at the company with BlackBerry. And so we can see that the target is we want to predict the volatility of the BlackBerry stock price. And we can see that during the 2008 crisis, we seriously underestimate volatility. And it's, of course, 2008 is a period of very high volatility. And we seriously underestimate the volatility in 2008. And then it's overestimated in 2010 and so on and so forth. So we see that the nominal level is not close to 90%. It's close to 90%. It's not 90%. But we see enormous swing around the mean. The blue curve is the curve that you get by being adaptive in this fashion and in the fashion I mentioned. And so what we can see now are the error rates that you get by dialing up and down the coverage alpha. And so you see that in all cases, Fannie Mae, of course, experienced huge swing during the crisis. This was a loan company. And what we can see that the blue curve swings around the nominal level of 90% and has much reduced amplitude. So it's very, very close to the target. Now, to show you how close it is from the target, I have actually plotted this gray curve. And what this gray curve is, it's the error process if the errors were IID with error 0.1. And so the local coverage would be, it's a smooth average of an IID process. This is essentially the gold standard. If each time you cover or not independently with probability 0.9. So this is your gold standard. And what we can see is that this gray curve is at least visually comparable with the blue curve, that somehow the blue curve has a level of performance that looks a bit like the performance you would get if you were if you achieve coverage 90% of the time in an ID fashion. So this is reassuring. Okay, so this is the same plot that we've seen before. And then on the bottom, what you see is how you dial up or down this parameter alpha. Okay, so there is a lot of theory that you can write about this. And I would like to refer people to our NeurIPS paper from this year. What you can show is you can show that on average, even though you have in the stock market enormous shifts, on average, you'll see that the average error is exactly what you want. Over the long term, the number of mistakes really will be 10% or 5% or whatever you want. And that holds without any distribution assumption of any kind. Okay, so that's reassuring. So over the long run, things are fine. Of course, we would like things to be fine, not over the long run, but at every time point. And in the paper, we say, well, how do you do an analysis of this kind? Well, we model things as a hidden Markov model where, we can go through regime changes. If you think about the stock market, and then we have data whose distribution depends on the state you're in. And then we were able to build a theory for hidden Markovs of this kind, models of this kind. Maybe in the interest of time, I will not go into the theoretical results, but there is quite precise theories that explain that, at any given time, I can maintain reasonable coverage if somehow this Markov model is applicable. This hidden Markov model is applicable. Okay. Going back to the election, and this is not the algorithm you saw implemented by the Washington Post. This is a different take on what John Chirian and Lainey Bronner have done for the data science desk at the Washington Post. But I want to kind of again illustrate perhaps the usefulness of this method in real world applications. So let's say that we want to, we look at the counties in the United States. Votes have been cast. Some counties have reported, and I want to predict the votes for, let's say, Joe Biden in a yet unreported county, or Donald Trump, or whatever. So you can first use a machine learning model to learn this quantity, which are the fractional change of the votes for the Democratic candidate between 2020 and 2016. And formally, this would be the votes between 2020 for Biden minus the votes for Hillary in 2016 over the vote for Hillary. So I have lots of demographics variables about each county, the median incomes, the educational level, the size, the population, the size of the largest cities, blah, 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 whether it's urban, rural, and so on. And based on these features, I want to predict this, that is how the Democratic vote will change between 2016 and 2020. And of course, now counties start reporting. And if counties were reporting at random, then the amazing thing about conformal inference is that, well, I could just apply it out of the box, because it would be like drawing balls from an urn. The theory will work. I can implement the CQR algorithm you've seen at the beginning of this lecture, and it will be totally valid. Here, the difficulty is that counties are not reporting at random. And, you know, smaller counties tend to report early, rural counties tend to report early, East Coast counties tend to report early, of course, for obvious reasons. And so here we're going to have a distribution shift. So I'm not pulling these counties out of the 4,200 counties that we have in the United States at random. They come in an order which has to do with their features and their characteristics. Here, you're going to see a simulation where East Coast counties are observed before West Coast counties. So I'm going to scan the United States from east to west. And what you see is when you apply this technology, and you can use your neural net or whatever you want to predict this quantity, right? This is where machine learning is. Use your features to do as good of a job to predict this quantity. But now I want to give you I want to do UQ. I want to say, well, yeah, but plus or minus what? So if you use the online method that I presented, the adaptive, what we call adaptive conformal inference, as we move through the night from east to west, we see a local average of coverage in blue, and that is using this dynamic scheme I presented. If you don't use a dynamic scheme, if you think that actually there is no distribution shifts, I can just assume that, you know, I pull them at random and I'm just going to apply conformal inference out of the box, then you would see that two things are wrong. First of all, you know, the nominal level will not be what you want it to be. And also you'd have, through the election, especially as you go through the Midwest, you would have enormous point in time during the night where you will be really not reporting things accurately. But if we use the dynamic scheme we have at the top, it seems that we have, again, and in gray, you see the random fluctuation of IID random variables with probability of success 0.9. We see something that is very much like this. Okay. All right. I have 15 minutes left. I can take questions now, or I can continue.
Well, we had a couple of questions. Why don't we take a couple of ones now?
Yeah, maybe we break. The last part of the talk has to do with something a bit different and something I'm excited about, which is joint with a group of Michael Jordan. And so we'll see whether we have time to go through it.
So this is one for Leonid Chinlevich, who says, this will likely be touched upon in the second half of the talk, but how would this idea apply to a standard two-class classification problem? More specifically, what would be the appropriate statement about the prediction's uncertainty?
So if you have, so I think this is a bit the limitation of this method. If you have two class, so first of all, there are extensions of this to discrete labels. So for example, we're going to see this in a minute. So your response Y might be categorical, which is this object a chair or a person or a car or whatever? If the categories are true, then this is where you start hitting the limits of these methods, because, I'm going to have to predict a 0 or a 1. And I want to do this with confidence. So if you have a very good machine learning algorithm, you might say, I'm 90% sure it's a 0, 90% sure it's a 1. Sometimes you might say, I don't know, so you have to report 0 and 1.
Here's another one from, sorry.
Yeah, go ahead.
Here's another one from an anonymous attendee. Can CQR be used to create meaningful high-dimensional confidence intervals, e.g., generating a confidence interval applied to the popular max activation method used to visualize neurons in a convolutional neural network, so we no longer get a point solution?
So I want to emphasize a key difference between this and classical confidence intervals. If I understand the question correctly, but I may not be understanding it correctly, there are parameters in your neural net that you would like to have, you would like to predict their values with some confidence, right? But these parameters really only exist in your head. They are not things you can touch. They are not things that I can measure. And I think in statistics, we're used to try to construct confidence intervals for parameters that depend on the models that you have specified, and whether they correspond to reality or not is sometimes debatable. What this is completely different. That is, there is an outcome of interest to me, which is how you're going to respond to this treatment. Will you be infected with the virus or not? And this is what we're trying to predict, not a parameter that we sort of constructed through a model, a real observable outcome. And maybe I want to thank whoever asked this question to clarify this extremely important distinction, that I'm interested in predicting outcomes, not parameters of a model that I created.
Okay, so if the person wants to clarify this, I encourage the person to write that in the Q&A, and we can follow up on that later on. But please continue, Emmanuel, with the rest.
Yeah. So maybe in the last 5 minutes, 6 minutes, I would maybe I try to be pedagogical. Maybe I was not, but I went a bit slowly so far. Now I'm going to go a bit faster to report on work with Anastasios Angelopoulos, Stephen Bates, Michael Jordan, and Li Hua on controlling arbitrary statistical risks. And maybe I had an introduction at the beginning. I'm going to skip this to just really go to the heart of the matter, which is this, that, we've talked a lot about miscoverage. So for me, the error the statistical quantities that I was interested in controlling was essentially a binary variable, the expected value of a binary variable. Are you in the set or are you not in the set? The miscoverage rate. And there are many other notions of errors that I might be interested in controlling. And so, for example, going back to the theme of this workshop, I might be interested in images, and I might actually be interested in detecting tumors, which is what you see on my little display on the right. And what is a notion of error you would like to control here? Well, maybe the false negative rates. So, you can tag each pixel as either being tumor or not tumor. And what the error metric you might want to consider is you want your false negative rate, that is the missing important pixels that are tumor pixels, to be low. Okay. And so, there's a notion of a statistical error that you would like to control. In this example, and this is not my work, it's work that was done at Berkeley last year. Maybe the false negative rate is what you want to control. So what I'm giving you is you're going to have to return a map of indicator variables, 0, 1, 0, you're not tumor, 1, you're tumor, and you want your false negative rate to be low. That's the goal. And the question is, can I tune a machine learning algorithm instead of controlling for miscoverage? Can I control perhaps more sophisticated notions of statistical error like the false negative rates? And so in the work we did with Mike's group and with Liwa, we looked at problems of this kind. And for example, let's focus on the false discovery rate. So, for example, what the false discovery rate might be is, I don't know, I give you an image and you want to detect objects in the image, and the false discovery rate would be the fraction of objects that you tell me are there when in fact they are not there. So this would be the false discovery rate. So let's say that we have a statistical metric, let's say the false discovery rate, which is really heavily used in a lot of applications. I have machine learning algorithms, and maybe these machine learning algorithms depend on tuning parameters lambda. And what I want, the problem we're looking at, is how should I tune lambda to be sure that the false discovery rate with high probability is below a nominal value. And so as a function of lambda, as the algorithm, as I looking at all my parameters in my algorithm, I can have the false discovery rate be, of course, depend on lambda. Of course, the false discovery rate is going to be 0 if lambda is such that I report nothing. I prefer not to say anything. But of course, I can go from not conservative, very conservative to not conservative. And of course, depending on how I'm going to tune the lambda, the false discovery rate will change as a function of lambda. And so maybe I have a test data set where, because the false discovery rate is the expected value of a random variable, the false discovery proportion that I can observe on each test image, I can get a sense of the false discovery rate by computing empirical averages. So for each value of the tuning parameter, here you see only one, but you can imagine that you have 1, 2, 3, or 4 tuning parameters. What you can do is you can actually evaluate empirically what you think the false discovery rate is. And what you would like now to do is, based on this empirical evaluation, you would like to report a set of parameters, lambda, and if you were to choose them, you would be sure that the false discovery rate would be below a specified target. So how are you going to do that? Well, here it's difficult because you see this estimate of false discovery rates are all dependent because they use the same test set. So all these averages that you're looking at are all statistically dependent. They are not independent because they use the same data. And so you have information about these errors and they're extremely correlated. And so the way we propose to do something like this is to go back to old ideas in statistics and treat and look at this as sort of a multiple hypothesis testing problem. So one thing that is interesting here is we're going to try to bring like machine learning and neural net and ResNet and all that apply to, let's say, medical images with very old ideas from the field of statistics centered around multiple testing. So what we can think about is we can think about a null hypothesis for each hypothesized value of the parameter lambda. And a null in here would say, the false discovery rate is too high, it's about alpha. And what we're interested in is we're interested in finding these parameter values for which we can reject the null, that we're very sure that actually the false discovery rate is below alpha. And so perhaps because I'm running out of time, I'm not going to tell you exactly how you do this, and I'll refer you to the paper to do this. But basically what I think a naive way to do this, if you're familiar with multiple testing ideas concept, you'd say, well, I need to test many lambdas at the same time, so I'm going to use some sort of a Bonferroni correction, and that would be ill-advised because you're going to end up with very conservative selections. You're not going to be able to detect a lot of interesting pixels, or you're not going to be able to detect a lot of objects if you follow such a strategy. because you're going to be so conservative. But what you can do is, you can use a lot of work that was developed in the context of clinical trials to actually examine your machine learning models and select parameters for which the error metrics you care about are under control. And so maybe I will not explain what these methods do. All I will say is that it is possible to leverage a lot of the stuff you're seeing routinely used in medical trials, in classical statistics, apply it in this context of tuning algorithms to achieve controlled errors in a model-free and completely agnostic way. The performance, the guarantees you get will not depend on the data generation mechanism or the algorithms you use. And so I'll skip this slide, which was an illustration of showing you how you can achieve this. What I will say is it's basically connecting two fields, one from statistics and clinical trials and pharmaceutical statistics and medicine with machine learning. And so we're trying to build a bridge between these two fields. What you can do at the end of the day, when you implement all of this and you understand all of this, is you can have a very complex image processing task. And your task might be this: I give you an image and you have three tasks to do. You have to locate distinct objects. You have to find for each object a precise set of pixels for each object, okay, which is sort of what you see on the right. And you're going to have to tell me what this object is. All right, so you see this in action. This is an image we get, and you use all the wonderful machine learning technology. At the end, I'm asking you to, essentially segment objects and tell me what they are. And you have to recognize as many objects as possible. And of course, each of these tasks, locate distinct objects, well, we have various statistical errors that we would like to control. So for example, to locate distinct object, I might be interested in recall, which is a different name for the true positive rate. For segmentation, trying to find what exactly each object is, I might be interested in the intersection over union, trying to identify as many pixels of the true object as possible. To tell me what object this is, I might be interested in coverage, as we discussed in the first part of the lecture. So we have very different tasks, very different error metrics, lots of parameters to play in. And so we can imagine that your whole processing pipelines has several modules. It has a segmentation module, it has a classifier module, it has lots of different modules, and you want to be able to control statistical error for each of these modules. And what the pipeline we're proposing is able to do is we'll say, well, we can do this. We can actually control the statistical error of each of these modules simultaneously. We can control the recall. We can control the intersection over union. We can control the miscoverage rate simultaneously by adjusting the parameter in a way that will depend on the selection I've shown you before. So this is a way which is extremely principled to say, well, here's what I can say about the future performance of your algorithm, looking at many things simultaneously. And because my time is up, this is my last slide. I think we live in a very exciting time where we see machine learning being applied to a lot of things. It's important to be able to understand the performance of this method, the uncertainty of this method, the performance of this method. And I'm very happy to see that there's a community of researchers who think deeply about these things. And with this,